All right, so this is 7-1 alpha. And like I said, we're going to go through this together. Now, this is like the chapter summary. These bullet points come up on every Google slide show. You need to take some time to see if you can identify what it's talking about. So the first thing is, we talked about this before, distinguish between a parameter and a statistic. What is the difference between a parameter and a statistic? Mima.
Statistic describes samples and parameter describes population.
Exactly. Alliteration. The statistic goes with a sample, the parameter goes with the population. Come down here. Distinguish among the distribution of a population. Well, we've done that. Distribution of population. Distribution of a sample. We've done that. And the sampling distribution of a statistic. We have not done that. That's what this is about. It's essentially this fourth bullet point, the last part of that sentence. That's what you're looking for today. We already knew that. That's what Tamima just told. And this is also a review. Remember, Roman letters for the sample, Greek letters for the population. If you see a Greek letter, that is referring to a parameter. If you see a Roman letter, that's referring to a statistic. So we're going to do the half of this one. Ready? Identify the population, the parameter, the sample, and the statistic. Just the top one. And it says, Gallup asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. Okay. So what do you have? You have a sample that represents the population. What is the population for A? Nope, I'm tired of talking to me. Get the game. What is the population? Amina. Thank you. It's all U.S. adults. And what are you doing? You're sampling 515 of them, so you can make a judgment. You can come up with a statistic that, if it's unbiased, will represent the parameter of all U.S. adults. The parameter is the proportion of all U.S. adults that believe in ghosts. The sample is the SRS of 515, and the statistic is 160 out of 515. Okay? Now, you also have these on the PowerPoints. You've got these tips. Well, when you're doing these PowerPoints, you need to be focused. Like there's a reason that's on here. So they're saying a lot of times people have trouble when they're writing an FRQ being specific enough. They said one hint is this. In order to describe the parameter, like if you said true mean, the reader knows that true mean means you're referring to the parameter. You just talk about mean, and you don't specifically say sample mean or population mean, then you're going to be penalized. Yes, we did this, alliteration. Now, ready? Think about this. sampling variability. So suppose we wanted to collect some data. I want to find out what proportion of students in the high school. So my population is SHS students. And I want to find out what proportion of SHS students bring their lunch. It might seem silly to you, but it's important to the Chartwells. They're going to have much food to buy. So suppose we did this. Suppose we randomly did a stratified random sample. We randomly identified advisories. So we picked at random these 2 senior advisories. Does it make sense to you, even if the 2 advisors had the same number of students, so they both have 18 children in there? Does it make sense to you that it's unlikely that the same number of seniors in each advisor would bring their lunch? It could happen, but it's not likely, yes? And that's sampling variability. It refers to the fact that different random samples of the same size, of the same population, could produce different values for a statistic. In one advisory, it's 12 out of 18 children bring their lunch. In another one, it's 10 out of 18. That is sampling variability. Now, this is a really good picture. Because what does it mean? What we told you before is, this is saying you have a sample mean of n equals 5. So the sample size is 5. So if you take the mean of size 5 from different samples, same population, different samples of size 5, and you plot those means, these are all X bars, then that would give you a better idea of you, the true mean. Because of sample variability, suppose we took a sample of size 5 and end up with this group. That's biased. It doesn't map onto the parameter which is in there. Does that make sense? So if you do this many times and you look at the distribution of those sample means, that would give you a better information of the true mean. But you have to understand, we haven't done this before. This is saying, instead of taking the distribution of a population or a sample, we're taking many samples of the same size and plotting those means and doing a distribution of that. So, here's an example, ready? You got these 4 kids, and we want to pair them up. Now, this is saying we're going to do all the possible samples of size 2. So there's 6 of them. How do we know that? Because it's 4 choose 2, which we can do over here. Here's the triangle. The 4 choose 2 is 6. 4 choose 0, 4 choose 1, 4 choose 2. 4 choose 3, 4 choose 4. Or we could go the algorithm, which would be 4 choose 2 equals 4 factorial divided by 4 take away 2 factorial times 2 factorial. Which means 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. 12 divided by 2 is 6. So there's 6 ways to pair up those children. A combination, order doesn't matter. Let's calculate the mean of each and do a dot plot. So there you got the shortest kid, 71, paired with the 3 brothers. Then the next kid is 75 in the order of birth. So we're not going to put 75 with 71 because that was already done. We're going to put 75 with the other 2 kids. We end up with 6 of them. Here's the means. We plot the means. That is a distribution of sample means. When they talk about the range, that's how far apart those are. So let's go to this one. You've got 500. No, I'm sorry. You get 200 chips in this bag. 100 are red and 100 are blue. Okay? And you take a sample of these chips. So this kid reaches in this bag, there's 100 red and 100 blue. The kid takes out 20, and instead of getting 10 and 10, they get 7 red and 13 blue. So the child wants to know, is that evidence that there's actually less than half of the chips in the bag are red? Or is that sampling variability? Make sense? Because you would expect, if you took 20 chips out of there, if half of them are red, you would get 10 red. You're not guaranteed to get that. So you got two possibilities. Jenna's sample, P hat. P hat means the sample proportion is less than 0.5 because of sampling variability, or maybe there really aren't 50% red chips in the bag. So here's what happened. They did a simulation. The software will do this over and over again. That's what this distribution would look like if they did 500 repetitions of a simulation of taking 20 chips out. So 20 chips out, and whatever proportion was red, that got plotted. So what's this one? This one is 1.5%, I'm sorry, 15% are red. Okay, so what'd you get? 3 out of 20. So this one time you got 3 out of 20, and then you did it 500 times altogether, and then these dots got all stacked there. You good? That would be a simulation if there really were 100 red and 100 blue in it. There's one dot on the graph at 8/10, one way over here. What does that mean? It means one time in the sample, one sample had 16 red and 4 blue. One time, out of 500. Would it be surprising to get what that child got? Ready? 35%. Because that child got 7 red, 13 blue. So here's 35%. So we count this and everything to the left of it. Is that surprising? Well, we can't quantify it. We just look at the heights of the bars. There's 4 bars altogether that are 35% or lower. That make sense? It's not statistically unlikely. So, because if we look at this table, look at the dot plot, the way Jenna, her samples here, because the heights of these 4 bars added up, do not give you evidence that there was less than 50% red chips in the bag. Now, don't worry about, I'd rather be more specific than that. We will get to actually quantifying things. We're not there. We're just trying to get a big picture idea. So, here's a summary. Ready? You got 100 blue chips and 100 red chips. Okay. Then what's this? These are 2 samples of size 20. One of them was 12 blue and 8 red. The other was 9 blue and 11 red. There are 2 samples out of the 500 in the simulation of size 20. And here is the sampling distribution. So this is p hat, 8 out of 20 gives you 4/10, so it's one of these dots here. This is p hat, 11 out of 20, this is one of the dots above 55%. Which one? Population, a sample, sampling distribution. Right? Of the sample proportion. So that earlier screen we showed you had all those X bars. These, in effect, would not be X bars. These would be P hats. But there's 2 things we're looking at. The mean of a data set or the proportions. So the earlier picture had those X bars, sample mean. This is sample proportion. So instead of X bar, it would be represented by P hat. And then another tip. Okay. So this is what we're trying to point out to you. Different SRSs of the same size. I don't think that's very good grammar here. Different same size SRSs. Different SRSs of the same size from the population produce different values for statistic. That's just sampling variability. There's nothing nefarious about that. Okay? So you're going to go to 2 problems. 7 and 13. Okay, so let's look at 7. 7 is about quiz scores, right? You have this group of 5 and you take 2 at a time. So fortunately, these children are alphabetical and they all have names that begin with the letters A through A. So here's A and B paired up, that's their mean. A and C, that's their mean. All the combinations. Combination would be 5, choose 2, which would be 10. So I put them in a list, the means in a list, and plotted the means. Now, you're not going to do you're not going to do a histogram on the calculator. You're just going to do a dot plot. You have them stacked up. What do you have? You have these 3 means that have happened twice, and 1, 2, 3, 4 that happened once. But again, that problem is about means, and the poker chip problem before that in the textbook was proportions. You have to go to 11. It's taking the data from 11. And it says, a newspaper article claims that 60% of students at a large high school do their homework. And there's 2,000 kids in the high school. So the school says 60% of the kids do their homework. And then 13, it says, some of the students in AP Stat are skeptical. So they do an SRS of 100 students. One SRS of 100 students. And found 45 of them did their homework. So first off, what would happen? Well, if 60 were true, the true proportion, we could do a software simulation and it would look like this. And that is repeated. Now again, this is a proportion, so these are all P hats. You get it over and over again with the software if the true mean were 60%. And the sample was 45%, which is less than 60. So what explains that? Well, one is 60% is correct, but you have sampling variability. And the other is 60% is overstated. But in this case, of the simulations, none of them were 45%. So it appears it's more likely that 60% is false. Make sense? See, when you did this simulation over and over again, and you plotted those t-hats, none of them made it that far to the left. So then C says, well, what's the dot? There's one dot all the way to the right, 0.73. Well, that is one sample, and all these represent sampling distributions out of 100 kids, one at a time. One of them, 73% of the kids, when the mean was 60, I'm sorry, when the center was 60%, the true mean is 60% of the kids in their homework, the true proportion, sorry. That one time the sampling spit out 73%. And there's 250 dots here. So 45% would be surprising because none of the 250 dots made it that far left. So that appears to be comparing the simple random sample from the statistics class to that software generated sampling distribution. That appears to give evidence that the school is exaggerating what proportion of their kids do their homework. Make sense? So that's that for 7.1 alpha.